Hey guys, in this video I will show you how to use Tricitor grammar parser that we developed in the previous video in a Rust project, which can be either a front end of a compiler or some tool that processes and analyzes source code like semantic analysis or anything like that. And also I show you some handful and useful macro I used in my Rust projects that work with syntax trees. So let's get started. In the last video, I didn't really show what the Tricitor parser publishing workflow looks like. So let me walk you through real quick. It's actually super simple, and all you need to use is the Tricitor workflow component and add your cargo registry token. So that's literally it. And if you want to publish your parser to npm or py, you just drop the right API key for those instead, and it simply works. All right, so here's how you actually use a Tricitor parser in a Rust project. Here we have two things you need to bring in. First, the Tricitor crate, that's basically the engine. It takes your custom parser and actually runs it to produce a CST. And second, the custom parser itself. In my case, it's a Tricitor inference, which I'm using to parse inference syntax. I already went over this work internally in the last video, so if you're curious about the structure, you can check it out. Having these two, we can actually run the parser. First, we need to instantiate a Tricitor language structure that defines how to parse the inference language. Next, we need the parser, a stateful object that is used to produce a parsing tree based on some source code, and install inference language into the parser. Then we execute the parser, feeding it to this source code. As a result, the parser returns a parsing tree, or a concrete syntax tree. Now we are ready to process it. So we take the root node and the tree and coupling it with the source code, passing it to the AST builder. A small note about the parsing or a concrete syntax tree. Here is the view taken from the Tricitor playground. In my previous video, you can find how to set up and use it. On the left-hand side, you can see the source code, and on the right-hand side, the parsing tree. This structure describes the particular concrete syntax in a tree-like structure. It means that it contains all tokens and symbols the parser traversed and tracked during the parsing process. Blue color here indicates node types. Usual font color shows named children of the node, and green color shows anonymous nodes that are specific to the parsed language. The parsing tree contains full information about the source code, so we can reconstruct the source code, usually except white spaces and comments, in its original shape, simply traversing the tree and omit every node. However, this data structure is not ideal for the analysis and post-processing because it's too specific, and it's better to distill it remaining only those data structures that you actually need. To go away from the parsing tree, the abstract syntax tree data structure is used. Well, it's still a tree-like view, but much succinct and easy to deal with. So here's an example of how AST is defined for inference. On the high level, it defines what syntax structures exist, for instance, statements and expressions. I use enums in a natural way for defining some data types. About data types from the type theory I have been sharing on my previous video. I will leave a link in the description. Two things to notice here. One, as you can see, the block type, literal, and type are defined from other enum arms. They are not RC. This is because they are enums, and with all arms following the same structure with RC used as an arm type. Why RC and not a box? First of all, we need a reference here because of the recursive nature of syntax tree nodes types. An expression, for example, most likely contains other expressions that can be included one into another. Because of this circular organization, references are required here since the size cannot be known in the compile time. Hence, stack allocation impossible because we don't know how deep to move the stack pointer. I prefer using RC instead of box, keeping in mind further semantic and other static code analysis phases. These procedures can be memory and computation intensive, so to reduce the memory bandwidth pressure and not making copies of box references when, say, iterating and passing children nodes, so on and on, reference counter looks as a better choice for me. Overall, AST forms the tree where the root is actually a source code file. Then, from top to bottom, filled with the nodes describing all elements such as imports, definitions, and so on. As you can see everywhere as references, I use RC. Of course, I can imagine some arguments against this approach, but at the moment I find it well balanced with usefulness and resources consumption. Let's move on and see functions that produce the tree. As we have already seen, the tree setter generates a root node, which we see here as well as the source code is passed to the build AST function. For semantic analysis, I prefer to add as much information about the actual source code as possible to the initial version of the AST tree. Here, the location of a node is taken from the reference to the node and the source code. I will show it in a moment. Source file is a root node that is filled with children of all other node types by iterating and recursively traversing all child nodes. These functions represent the node's traverse logic. If the node type itself is a substantial node, not an aggregation as an abstract definition or statement, we construct a structure of the node. For example, enum is constructed step by step, reading named or anonymous children in the given node. The node of type identifier is named as a name, so the function child by field name can be used to address this node. On the left side, you can see how it is defined in the tree setter grammar by using a field function. Since enum can have several variants and the number of variants can vary, what is done here is we create a cursor, an object that allows to manually traverse CST. Then, with this cursor, all child nodes named as a variant are collected and then processed to build an identifier representing an enum arm. As a result of the function, a reference counter to the enum struct is returned. A higher level constructions such as definitions or expressions are handled as follows. Pattern matching to the node kind according to the tree setter grammar node name, then colon is specific to the node type function and enum variant is returned. Now, the most basic functions that are used. Build identifier and get location. Identifier is nothing but an underlined string, so what's happening here is a node raw node text extraction. The location is an aggregation of all shortcuts to access information about the position of the node in source code. In my example, it's super explicit and suboptimal because it has a copy of the source code string, which means a tremendous waste of memory for keeping all these copies. I will optimize it for sure because it's enough to save only source code on leaves, which are either identifiers or literals. And for easy std out, debugging allocation implements display trait. Now let's take a look on the AST node type internals. This is a trait specific to the inference compiler, but actually I used it in my several other projects. So a node is a trait with the following functions defining itself: ID, location, node type name. Here an std any type name type is used to take an actual type name from the Rust code. Meaning, for the type with the qualified name as, for example, module AST definition struct myStruct, it returns the latter segment, which is myStruct. The children function returns a vector of references to nodes wrapped with the nodeKind type, which is an enum serving as a thin abstraction to generalize different AST node types. Actually, I was thinking about creating for every node a pair of enums defining its possible parents and children, which I find more reliable, but haven't implemented it at the moment. I assume the price for it will be a long code. Maybe some macro could help, but I'm not sure at the moment. nodeKind is an enum that I use as a universal type that I can cast any node to and from. This is an alternative to an abstract types in a way that nodeKind exposes universal interface trait node for any underlying type it holds. This structure actually enforces compile time type checking and eliminates dynamic dispatching. To make actual nodes definitions more succinct, I have the AST node macro. It takes a structure of a node and adds additional standard fields, ID and location into it. And to generate a standard implementation of the node trait for actual types, the AST node impl macro is used. It implements, following the AST node macro, a standard part of the interface, which is ID and location functions. The rest implementation functions remain as they are because they're specific for the particular type. The AST now macro is a bit lengthy, so I split it side by side. Here is the part that implements the same interface as exact node types implements according to the node trait. It makes possible to use AST enums as they were nodes by calling underlying node types. This is very convenient in generic algorithms where we need to iterate or traverse nodes regardless of their types. And as you can see, no dynamic dispatching happening. This is so because we literally call inner functions ID and location by referring to them. So we use enums only to be able to distinguish between node domains, let's call them like that. But internally, every node is a node trait. Then we're eligible for doing that. The compiler ensures correctness and does type checking, so it's perfectly fine. Here are several examples of AST node types. Enums are defining higher level node types, and because enums hold RC to actual types, we can transparently use other enums as values for enum arms. In AST nodes, only meaningful attributes are defined because standards are generated by macro. Similarly, node implementation requires only explicit children definition because the main functions are either have a default implementation or generated by a macro, and no procedural macro are actually used. Now let's have a look at what we can generate with all this. After running the build AST function, we can dump its result with surd to the JSON file. JSON works good and can give a nice visual clue about internal structure of AST. Although its value for debugging purposes might be questionable, but if you need to compare parsers output side by side after changes or need to transfer an AST code structure to some other tool, it can be useful. Internal structure of a user directive is virtually as we would imagine seeing it. And this is the case for all other nodes. So this is actually pretty much it for today. So we covered all those topics that you need to construct AST, such as how to install required crates into your Rust project, defined AST node types in a short form using some macro, and some tricks to address and operate with nodes as generic data types, and a build function that recursively traverses a result of the tree parser, concrete syntax tree. and produces the AST, which is ready to be analyzed, processed. What's that all about? We'll see in the next video. So please follow Inferrara on GitHub. Read about inference programming language, which is a specific language that we built to provide a way to developers to specify formal properties, propositions about their code, to certify the correctness of code using top-notch mathematical framework. Thank you.